Okay, getting there. Um, Working through our practice exam here. So moving on to our final page here of the practice exam. Question number 7. We've got a balanced equation there, so some kind of stoichiometry problem. And we're told iron 3 oxide reacts with carbon monoxide, and we've got a balanced equation there. We've got a reaction mixture with 22.55 grams of the iron 3 oxide and 14.79 grams of carbon monoxide, and we're asked how many grams of CO2 will be produced. So two different masses for the two reactants. This is a limiting reactant problem. So we're going to have to calculate how much CO2 could be produced from either of those reactants, figure out which one's limiting. That's how we'll get the answer to that first part of the question, right? Then we have some subsequent questions there about the excess reagent, right? And then a gas law related question there about the original sample. So let's start with those two samples though and see if we can work our way to figuring out which one's the limiting reactant and how much carbon dioxide will be produced. So 22.55 grams of Fe2O3, and we want to work our way to grams of CO2 to answer the second question. So I forgot my G there, but that's grams. First thing we'll want is the molar mass. So Fe2O3, 1 mole would weigh 203. I need to add this up, find it in the periodic table. So we'll do that over on the side. So 2 irons are in here. Iron is 55.85, so 2 times 55.85 for the irons. 3 oxygens, oxygen is 16, so 3 times 16 is 48. So add 48 to that. That gives us the molar mass for the iron 3 oxide. So 55.85 times 2, and then add to that 48. That is 159.70. So 159.70 grams on the bottom there. Then we can go, right, once our units are in moles, we can think about this balanced equation. For every 1 mole of iron 3 oxide, we should expect 3 moles of CO2. So 3 moles of CO2 would go on top. 1 mole of iron 3 oxide would go on the bottom. Right? And our first answer here was grams of CO2, so let's add that extra step and figure out how many grams of CO2 would be produced. So mole of CO2 would go on the bottom. Right? And in this case, carbon's 12.01, 2 oxygens is 32, so CO2 is 44.01 grams per mole. Right? And again, that's all coming from the periodic table, so if you don't know them off the top of your head, that's not a problem. You just find them in the periodic table. So multiply this out. And that one comes out to be 18.6, let's see, 4 significant figures, so keep that 4 grams of CO2. Now, maybe that's the right answer, but the thing about the limiting reactant problem is we don't know if it's the right answer until we do the next part, because maybe the CO was the limiting reactant. So maybe that's right, but maybe that's how much CO2 we'd make if we used all the iron oxide, and we don't use all the iron oxide, possibly. So we have to do the other calculation to double check. So we start also with 14.79 grams of carbon monoxide, and we want to figure out how much of the product could be made if we used all that up. So it's the similar steps, we just have to put in the right sets of numbers. So 1 mole of carbon monoxide, we want to compare that to what the weight of 1 mole would be. So 12.01 for carbon, 16 for oxygen. That one we can do maybe without writing it down on the side, is 28.01 grams in a mole. Looking at the balanced equation, 3 moles of carbon monoxide are going to react and produce 3 moles of CO2. So this factor will be 3 over 3, but I kind of still like to write it in because it does help us see how we're actually interacting with our units. We're at moles of CO2 now. So 44.01 grams of CO2 is 1 mole of CO2, right? And this will give us how much CO2 could be made if we use up all of that carbon monoxide. 14.79 divided by 28.01 times 44.01. And that is a bigger quantity, 23.24 grams of CO2. So what that tells us is this was our limiting reactant. The iron oxide is limiting. That's the one that's going to run out. It's going to run out when we make 18.64 grams of CO2. That means the carbon monoxide is in excess, right? Or it's the excess reactant. Now, that's our first answer. How many grams of CO2 will be produced? Right now, some of this data here is going to be helpful for the other answers. Now, I may have to go to another page, because I probably didn't give enough. If this was a real test, I wouldn't have given you enough room. How many moles of the SS reactant are left at the end of the reaction? Okay, so to figure that out, we need to do a couple things. We need to figure out how many moles of CO did we start with, and then also how many moles of CO did we use. So right here at the beginning of the problem, that will allow us to calculate how many moles of CO we started with, because that's the mass of CO and then converting it to moles. So if I just do those two steps, 14.79 divided by 28.01, that is how many moles I started with. So 0.5280 moles, right? And I'll put start in parentheses there just so we keep track of that. That's how much CO we started with. Now, how much CO we actually used will be related to the limiting reactant up here. So if I take that 18.64 grams of CO2, that will relate to how much CO was used in the reaction, because it'll be the amount of CO that was used up to make that. So some of those factors are already in here. I can just kind of put them in, drawing them from above. So I want moles of CO2 on top, divide by 44.01 grams on the bottom. From my balanced equation, 3 moles of CO2 for 3 moles of CO. So 3 moles of CO on top now, 3 moles of CO2 on the bottom. And that's what I want, is moles. So I can stop right there. 18.64 divided by 44.01, right? And then times 3 divided by 3, we just don't need to punch that in, is 0.4235 moles of CO, and that is how much was used. So we're actually asked how many moles of the excess reactant are left at the end of the reaction. We still need to subtract to do that, but if we take, see if I can find a spot to do this, the 0.5280 moles started with, subtract 0.4235 moles used, and that will give us how many are left over. And that is 0.1045 moles of CO left over. And that would be the answer to the second question up there. How many moles of the excess reactant are left at the end of the reaction? Now, the third question, and I'll slide to some clean paper for the third question. What would be the pressure of the 14.79 grams of CO in a 1 liter container of at 298 Kelvin? That's just a gas law problem, right? And I think we can fit it up here where the name box is. This part of the question that we already calculated will be helpful, because it says what would be the pressure of the initial sample of CO. We already figured out that's 0.528 moles of CO. If we've got moles, we've got the volume of 1 liter, and we've got the temperature of 298 K. That is enough to solve for the pressure. So up here at the top, and make sure we can see that good, if PV equals nRT, and we want to solve for P, we can just rearrange there by dividing through by V. P is nRT over V. right? And because of the way the first couple pieces are set up, we have that information. So N here is 0.5280 moles. R is 0.0821 liter atmospheres per Kelvin mole, although I'm going to leave that off here in this problem. Since we've done that enough times, I think we're familiar with how they cancel out. Temperature in Kelvin, and volume is just 1 liter there on the bottom. And it was written out as just 1 liter, but let's assume that that means it's an exactly 1 liter container and that it's not going to limit us to 1 sig fig. So 0.5280 times 0.0821 times 298, and then we don't need to divide by 1. That would be 12.91. So we'll stick with 4 sig figs from our quantity of moles there and assume that these others are exact. And that would actually round up to 12.92 atmospheres, since that is the pressure. So that would be the final answer there. What would be the pressure of that original sample if it was in a 1 liter container at 298 Kelvin? Okay, a lot going on there, right? Realistically, on a test, that should probably be at least 2 different problems. Maybe one is the stoichiometry, another is the gas law problem. But in the practice test, we're trying to make sure we practice all of the relevant skills for the test. So that's a good length for this video. We can probably do the last 3, which are related to the different reactions we are trying to evaluate, in the last video.